Hello everyone, this is BV Ramat. Today we are going to discuss the next part of the current electricity, that is about resistivity, the temperature dependence of resistivity. The next concept is temperature dependence of the resistivity. See, the electrical resistivity of the material is already learnt in the last concept, that is rho is equal to resistivity is represented by the symbol rho. Rho is equal to m divided by n e square tau, where n is the number of free electrons per unit volume, tau is the relaxation time, e be the charge of the electron, and m be the mass. So this is already well known concepts. It's learned in the last concept or last session. Thus, the resistivity rho, which is depends on the two parameters of materials, namely n and tau. N is nothing but number of free electrons per unit volume, tau nothing but relaxation time. See, the variation of resistivity of a material with the temperature is different for different materials. So, this is different for different materials. Materials means you can consider as a metals or semiconductors, like that. See, we will explain with one by one with example. First, A, in which A thing is metals. First, we will discuss the in case of metals. In the metals, the density of electron is n, does not changes with the temperature, but the relaxation time tau decreases with increase in the temperature. See, in the metals, the number of free electrons is constant with the temperature, but so tau, that is the relaxation time, decreases with increase in the temperature. How means, in the metals there are n number of free electrons, so many number of free electrons are available. As the temperature increases, its kinetic energy increases. As kinetic energy increases, its velocity increases. See, if the velocity increases, the collision between the molecules increases. Then the time taken between the two successive collision, that is a relaxation time, is decreases. Hence, so the n means number of free electrons in the metals remains as it is with the temperature. So does not change with temperature. But relaxation time tau decreases with increase in temperature. First thing. Before, electrical resistivity rho of a metallic conductor increases with increase in temperature. So therefore, that is first thing. Before that, we should note that one more thing. The electrical resistivity of the metal or a metallic conductor increases with increase in temperature. As relaxation time decreases, its resistivity increases. See, that is the concept. In the metals, what happens here, the electrical resistivity increases with increase in temperature. So it's asked in 1 mark question in the annual question paper. See, over a limited range of the temperature, which does not too large, the resistivity rho of the metallic conductor at a temperature T is given by. So that can be determined using a formula, that is rho is equal to rho naught 1 into rho is equal to rho naught into 1 plus alpha T minus T naught. That is, say formula is rho T is equal to rho naught into bracket 1 minus alpha T minus T naught. Here rho T nothing but resistivity at a temperature T. Rho naught is the resistivity at a temperature T naught. Alpha be the temperature coefficient of resistivity. See, for a metallic conductors, alpha is positive and rho increases with increase in temperature. Nothing but resistivity increases with increase in temperature. For a metallic conductors, alpha is positive and resistivity rho increases with increase in temperature. See, in the second figure, that shows the variation of resistivity of a metal with the temperature. See, this is the y-axis along that shows the resistivity, along x-axis that represents the temperature. The graph is a straight line over a limited range of temperature. So this graph is a straight line over a particular limit of temperature. On the linear portion of the graph, the resistivity rho naught is resistivity corresponding to the reference temperature. See, for in the graph, so actually the linear portion, what it indicates means the rho naught, that shows the rho naught. It is the resistivity corresponding to reference temperature. For alloys, so that is in the first graph, that shows about the alloys. For alloys such as a nickel, manganese, constantan, like that, the graph is shown. So in the first figure, like this, that will be like this. But for the semiconductors like a carbon, germanium, silicon, the density of electron is n, that is increases with increase in temperature, but the relaxation time t decreases in the semiconductor cases. But the effect of increase in the n or number of free electrons is much higher than the effect of decrease in tau, that is the relaxation time. As a result, the resistivity rho of a semiconductor decreases with increase in temperature. See, the here in the case, the resistivity of a semiconductor decreases. See here in the diagram, third diagram, that shows, so the resistivity of a semiconductor, that is a decreases with increase in temperature. As temperature increases, its resistivity decreases, as shown in the figure 3. As the temperature T approaches to 0 Kelvin, the resistivity approaches to infinity value. Hence, the semiconductor at room temperature behaves as an insulator near 0 Kelvin temperature. See, the next concept is the variation of resistance with the temperature. Here, since we know the formula, that is the resistance formula, that is R is equal to rho L divided by A. The resistance R is directly proportional to resistivity C. So if these two considered as a constant, then in such a condition, then R is proportional to rho, that is resistance is directly proportional to resistivity. That means the dependence of resistance on temperature is similar to that of the resistivity. In the linear region, for a metallic conductors, the resistance R at any temperature T is given by, say, at any temperature for the linear region, in case of metallic conductors, the resistance value is, so the resistance R at particular temperature T is equal to R naught into 1 plus alpha T minus T naught. This is the formula to find the resistance corresponding to temperature. That is equation number somewhat 3.17, where R naught is the resistance at a reference temperature T naught. At particular temperature T naught, its resistance is considered as a R naught. The T naught value is equal to 273 Kelvin. Since 273 Kelvin is equal to 0 degree Celsius, so we can write this expression as, so this expression can be written as RT is equal to, R small t is equal to R naught 1 plus alpha T. See, where RT is the resistance at any temperature T degree Celsius and R naught is the resistance at 0 degree Celsius. Alpha is known as a temperature coefficient of resistance of a conductor. See, so as per this condition, RT is considered as a resistance at a temperature small t degree Celsius, then R naught is the resistance at 0 degree Celsius, then we know the temperature coefficient of resistance, that is as an alpha, then the above equation is considered as a RT is equal to R naught 1 plus alpha T. Then from above equation, from equation number 3.18, we can write it as, if you want alpha, then it becomes, that is RT minus R naught divided by R naught into T. How means? So you can multiply this R naught to this bracket, that be equal to R naught into 1 R naught plus R naught alpha T. Here already RT is there, then you can send R naught to LHS side, it becomes RT minus R naught, then R naught alpha T, in the R naught alpha T, alpha leave there, then RT send it to LHS side and it will go to denominator side, then it becomes alpha is equal to RT minus R naught divided by R naught into T. Thus, the temperature coefficient of resistance of a metallic conductor is defined as, see, we know that we already defined that alpha is the temperature coefficient of resistance. Hence, that definition is the temperature coefficient of resistance of a metallic conductor is defined as increase in the resistance per unit original resistance per degree Celsius, or you can take it as a Kelvin. Kelvin rise in temperature, that is what we can call it as temperature coefficient of resistance. The temperature coefficient of resistance, that is equal to, so we can take it as the increase in the resistance per unit original resistance. See, so increase in the RT minus R naught, that gives the increase in the resistance per divided by R naught is the initial resistance per initial resistance per degree Celsius. See, temperature is given here, that's why it is per degree Celsius or per Kelvin, rise in the temperature. So, as per this equation, this is the definition. Then alpha is equal to, this can be written, we can write like this. So, one more term, the SI unit of this temperature coefficient of resistance is per degree Celsius or per Kelvin. Then if R1 and R2 are the resistances at a temperature T1 and T2, as like this we took here RT is a resistance at temperature T degree Celsius and R0 is a resistance at 0 degree Celsius, like that. Now we are considering R1 is the resistance at T1 degree Celsius, R2 is the resistance at T2 degree Celsius. Then alpha value is equal to alpha, the rise in resistance, see here increase in resistance, that is R2 minus R1, then R1 T2 minus R2 T1. So this expression can be written as alpha is equal to R2 minus R1 divided by R1 T2 minus R2 T1. If R0 and R100 are the resistance values, like this. There is one more example like this. Here RT is a temperature at T degree Celsius and R0 is a temperature at 0 degree Celsius, like that. Here R0 is a temperature at 0 degree Celsius and if R100 is the resistance at 100 degree Celsius. In such a condition, the equation becomes, so that is so then in such a condition the equation can be taken and the temperature can be determined by the formula. In such a condition, see here RT is the resistance at any temperature T degree Celsius. Now T is equal to RT minus R0 divided by R100 minus R0 into 100, that gives the temperature in degree Celsius. Then the next one is electrical energy and power. See, electrical energy and power concept now we want to explain. Let us consider a conductor in which current I is flowing from end A to end B. See, let us consider a conductor, this is end A and this is end B. So the direction of flow of current from end A to B. Hence now again I am explaining now. Consider a conductor, this is a conductor in which current I is flowing from the end A to end B. The current I is flowing from end A to end B. The electrical potential VA at the end A. Here the potential at end A is taken as VA. VA is the potential at end A is higher than the electrical potential VB. So as compared, this is the potential at B end, and so VA is greater than the VB. The potential difference between end A and end B of the conductor is equal to the potential difference V is equal to VA minus VB. See, that is VA minus VB, that is a potential difference between ends of the conductor. See, in a time t, so that is a small interval of time t, that is taken as a time taken, can small interval of time can be taken as a delta t. See, in a time in a small time interval, sorry, in a small time interval delta t, the amount of charge flowing from the end A to end B is equal to, within the small interval of time delta t from end A to end B, so the charge flowing is equal to, that is delta q is equal to I into delta t, that is because we know the formula. So rate of flow of charge is equal to current is equal to q divided by t, then q is equal to current into t. Hence, so this is the formula. Here, the within the time interval delta t, the amount of charge flowing from end A to end B is equal to, as per this, amount of charge flowing from end A to end B is equal to I into t, that it can be written as I into delta t. The potential energy of this charge at A is Va into delta q. The potential energy of this charge at B is Vb into delta q. Thus, the change in potential energy is final potential energy minus initial potential energy, that gives change in potential energy. Then change in potential energy is equal to Vb into delta q minus Va into delta q. So final potential energy is equal to Vb into delta q minus initial potential energy is equal to Va into delta q. Then delta q is a common term, keep it outside. Then remaining term Vb minus Va. So Vb minus Va into delta q. Now see here, Vb minus Va. So we know that this is, you can take it as a potential difference. The potential difference V can be written as Va minus Vb. But we have now Vb minus Va, that's why this can be taken as minus V. Hence, in place of Vb minus Va, you can take it as minus V, and delta Q keep as it is. So the above equation becomes, then minus V keep as it is, in place of delta Q substitute this value, that is minus V into I into delta T. Since the charge in the potential energy is a negative here, the charge in the potential energy, that is a negative, there is a decrease, that means there is a decrease in potential energy. The negative sign in the equation that represents decrease in the potential energy. If the charge moved through a conductor without collision, their kinetic energy would changes, so that total energy is unchanged. In other words, see here, so in the above concept, the potential energy decreases, but if the charges move through the conductor without collisions, if the charge moving through a conductor without collision means definitely there is no change in the, there is no change in the actually without collision means there is an increase in the kinetic energy, decrease in the potential energy, but the total energy remains as it is. In other words, decrease in potential energy of the charge would be equal to increase in the kinetic energy, that is delta k, that is delta k equal to delta u, that is equal to, so V into I into delta t. But it is found that for a given potential difference, the charges move from one end to another end with a steady drift velocity. This is because of the collision with the atoms and ions. As the changes, actually here there is a change in the velocity because of the collision. As the charge move through the conductors, so this is happens, that is collision happens. It means that the kinetic energy gained by the charges is shared with the atoms or ions. As a result, atoms vibrates more vigorously and the conductor heats up. Thus, in actual conductor, the amount of energy dissipated as a heat during the time interval of delta t, that is equal to, so that change W is equal to, actually that equation is equal to delta W is equals to Vi into delta T, V into I into delta T. So this is the amount of heat or amount of energy dissipated as a heat in case of conductors. The power dissipated is equal to energy dissipated per unit time. We know that power nothing but energy per time. So that is we can call it as power. Then the power dissipated is equal to energy dissipated per unit time. See, this is the energy dissipated per unit time. Power dissipated is equal to, so energy dissipated per unit time, that gives here, that is, this is a energy dissipated, that means divided by time, that gives power dissipated. Delta T get cancelled, remaining term is V into I, that is given here. The power dissipated is equal to energy dissipated per, see here I'm explaining now, the power dissipated is equal to energy dissipated per unit time, and it's shown in the figure, sorry, it's shown in the given expression. P is equal to, that is delta W by delta T, that is then delta W is equal to here, that is Vi delta T, and divided by delta T, delta T get cancelled, remaining term is voltage into current. This is the power dissipated equation. Thank you.